Today I am going to speak on free vibration. The study of vibration is concerned with the oscillatory motion of bodies and the forces associated with them. You might have seen number of bodies which keep on oscillating. In some bodies, even if there is absence of force, they keep vibrating for some time. For example, if you have a tight string and you displace it slightly, then after you remove the force also your hand, then also it will keep vibrating for some time. Similarly, if you have a spring mass system, you displace the mass slightly, it will start oscillating. So there are these examples that without presence of any force, the body is vibrating, but at the same time you may have another example that there is a disturbing force. The force is like if you would have travelled in a bus. Now the bus is travelling, road is rough, so because of the rough road, the forces are transmitted through your tires and they come up to the seat, so you feel those type of vibrations. So there are the vibrations, they may be because of some external force or without external forces also, that body can oscillate between two positions. The study of vibration is divided into two general classes: free vibration and forced vibration. Free vibrations take place when a system oscillates under the action of forces inherent in the system itself and when external impressed forces are absent. If there are no forces, then body will obviously be in equilibrium. Therefore, there must be some forces which will cause the acceleration of the body, and body's velocity will change, like that it will keep vibrating. However, there are no external forces. The system under free vibration will vibrate at one or more of its natural frequencies. Now, if we take a spring mass system and disturb it for some distance, that means we displace the mass by some amount, then in that case there is this one motion of the mass starts, and this is called free vibration. The spring force is always present, and at the same time you have inertia force. Body is under equilibrium under the spring force and inertia force. So it can be seen that it starts with with one particular natural frequency. That natural frequency is the property of the system. It is independent of how much you have displaced. That is, so therefore that is this thing. So we are interested to find out the natural frequency. Now let us go to the next, this one slide. Vibrations that take place under the excitation of external forces are called force vibrations. When the excitation is oscillatory, the system is forced to vibrate at the excitation frequency. If the frequency of excitation coincides with one of the natural frequencies of the system, a condition of resonance is encountered and dangerously large oscillations may result. You may see that suppose there is a spring mass system and you apply some oscillating force. In the beginning, the motion can be of some different kind, but after some time the system will vibrate only with the natural frequency only with the frequency of the forces itself. Whatever forces you have kept, so it will vibrate with that. That is the in a steady state, the frequency of excitation coincides with one of the natural frequencies of the system. Now, there can be, in a vibrating body, can vibrate in a number of ways. However, first we will study that very simple case, that is called simple harmonic motion, in which that displacement can be represented by a sine function or a cosine function, means because sine theta is equal to cos 90 plus theta. So, simple harmonic motion, a body is said to have simple harmonic motion if it moves in a straight line such that its acceleration is always proportional to its distance from a fixed point and is directed towards the fixed point. This is the one definition of simple harmonic motion. In this, let us pay attention to each and every part. The body has to move in a straight line. That means if you have a spring mass system like this, now here this mass may vibrate like this, it may move, it moves in a straight line, therefore this is satisfied. So, this type of motion can qualify this one for simple harmonic motion. Acceleration is always proportional to its distance from the fixed point, that is the another condition, and is directed towards the fixed point. If the acceleration is not directed towards the fixed point, or at least say one particular point, then body will not come back to that point and the vibrations will not take place. So, that condition is also required. Now, we say that suppose you might have done one experiment, this pendulum. Now, pendulum is attached. If you slightly disturb it like this, it goes to new position, and then if you release it, it comes back, but it overshoots the middle position, reaches here. It keeps oscillating. Now, this moves here, naturally that this ball is moving on a arc. It is not moving in a straight line. So, it should not be a simple harmonic motion. However, you can see that if angle theta is very small, then it can be considered a straight line only. This segment, if you take a bigger circle and cut it here, a small portion, that will appear more or less like very close to a straight line. Therefore, it is approximately simple harmonic motion can be obtained by this. So, let us now oscillatory motions may repeat itself regularly. Suppose you have force vibration. Now, then such as spring mass, okay, this is, or even if that in free vibration you have a spring mass system, it may repeat regularly. We know that it goes, and after say from at 0 second it was here, at 5 second it went there, again after 5 more second it came here, then it went here. So, this type of behavior keeps continuing, or it may display considerable irregularity, like in earthquake vibrations are there, but they are irregular. Now, when the motion is repeated in equal intervals of time, it is called periodic motion. That equal interval of time, then you have periodic motion. The repetition of time t is called the period of the oscillation, and its reciprocal f is equal to 1 by t is called the frequency. So, t is the time period, f is the frequency. If the motion is designated by the function xt, then a periodic motion must satisfy the relationship xt is equal to xt plus t. T is the time period. At time period t, it should come back to the same position. So xt is equal to xt plus t. That is the condition for a periodic motion. Now, simple harmonic motion is represented, which is a periodic motion, is represented as the projection on a straight line of a point that is moving on a circle at constant speed with the angular speed of the line OP designated by omega. That means the simple harmonic motion, this is the, say there is a circle on which a particle is moving. It is connected by a string. You can assume that in a horizontal plane, attach a string with the mass and it is moving in the circle. So at any, if it starts at time t is equal to 0, this is 0, and then theta at time t is equal to, then theta is equal to omega t, where because we have said that, let us say that it is moving. So its angular position at any instant is indicated by theta is equal to 2 pi, theta is equal to omega t. Why theta is equal to omega t? Because at any, it is moving with a uniform, this one velocity. So at any point that between two time intervals, the displacement should be same. So omega must be some constant. So theta is equal to some constant times time. So this is the thing. Then what you do, that draw a, this one, projection. So this point may be called O, this may be called P, this may be M. Now study the motion of M, how the point M moves. Don't study the motion of P, study the motion of M and see what type of motion is this. P is obviously moving in the same way it is going, but the M is like this. In the beginning, M was here because P was here, so P. Then as it moves here, the M keeps rising, and finally when P is here, then P and M coincide and M goes here. After that, P goes from here to here, then M will move from top position to here, then P goes from here to here, M goes from here to here, then P goes from here to here, then M goes from here to here. So naturally you have, when it is completing a circle, by that time M has gone from this point to this point, came back from this point to this point, came back from this point up to this point, and then went to this point. So this motion is a oscillatory motion type. In one revolution itself it went from here, came here, then this, like that. So this type of motion will repeat. Now therefore, now with the angular speed of the line OP designated by omega, the displacement x can be written as x is equal to a sin omega. That we can write displacement of this point can be written x, because see a sin omega t. If we say that a is the radius, then this is naturally that this will be a sin omega t, theta is equal to omega t, and therefore acceleration is x double dot is equal to minus a omega square sin omega t is equal to minus omega square x. Thus, a characteristic of simple harmonic motion is that the acceleration is always proportional to displacement pointing opposite to this displacement. If x is equal to a sin omega t, then x double dot acceleration will be minus a omega square sin omega t, that is minus omega square times x. Therefore, in a simple harmonic motion, acceleration is proportional to displacement pointing opposite to the displacement, okay, and it is that is the this thing. So that means pointing towards the origin, whatever you have taken. Now the quantity omega is generally measured in radians per second and is referred to as the circular frequency. Sometimes term circular is dropped and it is just called frequency only. Since the motion repeats itself in 2 pi radians, we have the following relation: omega is equal to 2 pi by t is equal to 2 pi f. See, omega t must be same as omega t plus t, where t is the time period, and not omega t, it is sin omega t. Sin omega t is sin omega t, because sin this one we know that it is same as sin omega t plus 2 pi. So what happens that you have 2 pi is equal to omega t, where t is the time period. Therefore, omega is equal to 2 pi by t. 1 by t is called the frequency. Therefore, this is can be written as 2 pi f. In every actual case of free vibrations, there exists some retarding or damping force which tends to diminish the motion. Motion, you know that otherwise your body will always keep oscillating. You have seen that if you take a tight string, displace it slightly, it keeps vibrating for some time, but after that it stops. Why? Because of the presence of damping. Similarly, if you take that simple pendulum, displace it slightly, it keeps oscillating for some time, and after that it stops. Why? Because of the damping. So this is therefore, if the damping forces are small enough, they can be neglected, okay, because they are very small. So sometime means we can study for considerable period of time, the motion keeps taking place and it can be neglected, okay. Then moreover, it is very from designer's point of view, it is conservative first to study that the motion without damping, and after that we see what is the effect of that damping. Damping will have effect on reducing the vibration. So this is the this thing. Now vibrating system is modeled by a spring mass system in its most simple form. You can take a spring and hang it from a ceiling. At the other end, if you put a mass, it becomes a spring mass system, and you can study it, this one. But it is not that it is the study of this spring mass system is limited only to this type of thing. Many other systems can be approximated by a spring mass system. You can always say that this is something like a spring. Suppose tight string is there, you displace, so you can say middle point, it behaves like a as if there is some spring. Similarly, if you have a rod and you are continuous rod, and if you are pulling by a force P, here also it displaces because of Hooke's law of elasticity, remove the force, it goes back. So it is basically a type of spring. The rod also can be modeled by a spring. Similarly, the mass may be distributed, but mass you can concentrate at one point, so you can make a simple model of that real system. Let us derive the equation of motion for a spring of spring constant K. Now one end of spring constant K is fixed and a mass is attached at the other end. So now when you put that mass here, there is a displacement. This is the static displacement delta D. This is the equilibrium position. You may say that at this point W will be equal to K delta. Make the free body diagram of this one. So this is mass, this is W, and this is K delta. So it is in equilibrium. Now disturb it slightly. You give the motion x here. Then what happens? That the total restoring force now is what? Spring has stretched by an amount K delta plus x. Therefore, this is K delta plus x is equal to W, and this is x dot, this is x double dot. X dot denotes velocity of that mass, x double dot denotes the acceleration of that. Forces have been shown here, W and K delta plus Wx. Now we see that W is equal to K delta, but here this side there is a force W, other side the force is K delta plus x. Naturally it is unbalanced. So unbalanced amount is what? Kx. So that is a restoring force that will try to bring it back to the original position. Now here, so now in the free body, so let us summarize this. The mass is being pulled by gravitational force W of magnitude mg. Due to this spring stretches, the free body diagram of the mass is shown in the middle of the figure. This figure, the mass is balanced due to gravitational force and spring force. If the static deflection of the spring is delta, then K delta is equal to W is equal to mg. Now if the mass is pulled down by a distance x, the spring force becomes K delta plus x. However, the gravitational force is mg only, which is equal to delta. Thus there will be a net vertical force upward which will start the motion of the mass. Applying Newton's second law of motion, mx double dot, mass times of acceleration, is equal to net force acting on the particle, that is W minus K delta plus x, or mx double dot is equal to minus kx. This is the equation of the motion. So we observe here that x double dot is equal to minus k divided by m into x. K by m is a constant, it is a system property. K is the spring stiffness of the system and m is the mass of the system. So this is constant, therefore acceleration is minus constant times x. Acceleration is proportional to x and it is directed towards origin because it is negative sign, and the motion is obviously in a straight line because we are talking about x coordinate. If the motion was in 2 coordinates, then we would have used x, y, and this is the thing. So this is the simple harmonic motion. Now let us, if we just define the circular frequency omega n by the equation n, let us say omega n square is equal to km, or consider that since k times m is a constant, therefore let me represent it by omega n square. Okay, time being, let us consider it a constant. The equation of motion becomes x double dot plus omega n square x equal to 0, or x double dot is equal to minus omega n square into x. Now this is since the now it has the following general solution. If you solve this equation, you can say this will be x is equal to a sin omega in t plus b cos omega in t. That is the general solution of this type of problem. You can this from differential equation or substitute this equation into the that previous equation. You see that the equation is satisfied. So the general solution of this equation is basically a sin omega in t plus b cos omega in t. The constants a and b can be determined from the boundary condition. For example, at t is equal to x is equal to 0, if you put that boundary condition, then x0 will be equal to b, because what will happen, put t is equal to 0, so x0, x at 0 is equal to, this is 0 and this becomes b cos omega, so x0 is equal to b. So that is one thing, and we see that it is basically sin omega in t. This naturally has got a period of basically 2 pi omega, because you know omega n must be, so this must be the frequency, because omega n it repeats, so sin omega n t is equal to sin omega n t plus t, capital T. Therefore we can say omega n into t is equal to 2 pi, or omega n is equal to 2 pi by t, where this is time period, so time period is equal to 2 by omega n. This is the thing. Now here, so let us say at t is equal to 0, x is equal to 0 and x0 is equal to b. Similarly, x dot is equal to a omega n cos omega n t plus b omega n sin omega t. At t is equal to 0, x dot is equal to x dot 0. Therefore, x dot 0 is equal to a omega n. If you put this thing, because this term at t is equal to 0 is 0. So therefore, a is equal to x dot 0 in divided by omega n. Now therefore, thus the general solution of of this problem can be written as x is equal to x dot 0 divided by omega n multiplied by sin omega n t plus x0 cos omega n t. So here we see that this is the general solution of the problem. If initial velocity is 0, then this will be the solution. If initial displacement is 0, only you provide the velocity, then this will be the solution. The natural period of the oscillation is omega n into t is equal to 2 pi, or t is equal to 2 pi divided by omega n, that means under root m by k. Therefore, what happens, the time period is proportional to 1 by under root k. It is proportional to under root m. If you take a spring mass system and suppose spring is very stiff, k is very high, then time period will be almost 0. That means motion, it will immediately come back to the same position, and this is the thing. So time period is 0, it vibrates, and if k is equal to very small, then time period becomes very high, and the similarly about the mass, so it is like this. Now natural frequency is given by Fn is equal to 1 by t, that means it is 1 by under root k by m. So this is the type of that motion, and it keeps occurring. So this is simple equation of that. Now we have to talk about that viscously damped free vibration. Now in previous example we considered only the restoring force of the spring, that is kx. Now we are going to consider damping also. Viscous damping force is expressed by the equation F is equal to cx dot, where x dot is the velocity of this system. We should also put maybe here minus Cx dash, because it is opposite direction. So this is that way. Then we represent this system in which viscous damping means damping, that means resistance is proportional to the velocity, but in the negative direction, minus Cx. So that means acceleration is proportional to this is force, for damping force is proportional to this one. Ft in this is take the mass, then represent by spring. Then again we have a dice part. Now dice part is one thing that suppose you take a system part in which is filled with oil, and in this that a piston is moving. That is the thing. So this type of system is called dice part, and here the force is proportional to the velocity more, because you know that in a this one viscous material, that if object is moving, therefore the force is proportional to velocity, and we can say that here we can put a Ft as the force acting downward on the mass. Actually in any you will not observe that in a system we always have dice part, but we are only modeling. We will see that effect, the same type of effect which this dice part provides, that may be provided by some other mechanism. Like if a cantilever beam is vibrating, so many particles are having that influence. So this is very complicated, but we can actually put like this. So therefore now equation of motion is mx double dot plus cx dot plus kx is equal to Ft. That means, because if we can apply the D'Alembert principle, or we can say the F applied force, or we can say like this, mx dot Newton's law mass times acceleration is equal to Ft minus cx dot minus kx. Now for free vibrations, Ft is equal to 0. Hence mx double dot plus cx dot plus kx is equal to 0 for free vibrations. So this is the equation for free vibrations in the absence of damping. Now let us assume that x is equal to a into e to the power st, where s is any number. So it is say this is any variable I have defined. Let us assume that one solution is x is equal to a to the power st of this solution. So see what happens. We have to put this value in this expression, then we see that ms square plus cs plus k e to the power st is equal to 0. This equation has been put, which is satisfied for all values of t when s square plus c by ms plus k by m is equal to 0. Then it is satisfied for all values of t. So this is that type of thing. Otherwise because est cannot be 0, e to the power st cannot be 0 except when t becomes minus infinity, this cannot be 0, become 0. So therefore this must be equal to 0. That means this equation is known as characteristic equation, and it has two roots, s1 and s2, given by s1 is equal to minus c by 2m plus under root c by 2m whole square minus km. These are this is one root s1, and similarly s2 will be equal to minus c by 2m plus under root c by 2m square minus km. Okay. let me show you some more steps. Now you have got two roots of this problem, that means both are the solutions. Now we assumed that the solution was x is equal to a e to the power st, that is, but it has got two roots. So therefore the solution will be what? That solution can be written as a e s1t, this also satisfies, and b s e s2, that will also satisfied. So therefore we can say a plus b e s2 t also satisfies this one. If you want to put, if you want only this, put a is equal to 0. If you want only this, you put b is equal to a, and b are just constants. Therefore x is equal to, now putting the value of s1 and s2, x can be written as e minus c by 2m into t, and this is a e to the power under root c by 2m whole square minus k by m multiplied by t plus b e to the power minus under root c by 2m square minus k by m, and t outside this square root term. So this is like that. So you get this one. Now we get this type of term. Let us see what happens when the damping term c by 2m square is larger than k by m. It is larger than k by m, then the exponent in the above equations are real number. This is a to the power some real number t, and this is equal to this one. And in this case, there are no oscillations are possible. It cannot provide the oscillatory motion. This case is called over damped case. This is over damped. So no oscillations are possible. Over damped case. When the damping term c by 2m square is smaller than k by m, that means this is smaller. Let me just, if it is smaller, then this will be called under damped case. This is under damped case. Under damped case. In this case, this is square root of a negative number, therefore it becomes imaginary number. This is this one. So therefore the exponent becomes, basically you can say, in this case I can write exponent becomes plus minus under root k by m minus c by 2m whole square. So this becomes like this, k by m minus c by 2m whole square, and this becomes imaginary number. Now now the term within the now therefore in this case what happens, see you have got S1, then S2 is equal to this one. Now you consider e plus minus under root k, this one, this can be written as cos under root k by m minus c by 2m square t plus minus I sin under root km minus cm square by t, because ei theta is equal to cos theta plus I sin theta. You have to use that relation. So now in this case, in the limiting case between the oscillatory and non-oscillatory motions, we have C by m square is equal to K by m, and the radical is 0. The damping corresponding to this case is called critical damping, that is Cc. So therefore Cc is equal to 2 by m under root K by m, or it is 2m times omega n, or this is 2 under root km. So critical damping is a property of the system. You know that it depends, that this is the thing. So K by m, that is critical damping. So any damping which is more than the critical damping is called over damping. Any damping which is less than the critical damping is called under damping. Therefore any damping can be expressed in terms of the critical damping by a non-dimensional number. We can say zeta. We say that zeta is equal to C by Cc, or we can use any other symbol, C by Cc, where Cc is the critical damping. If C by Cc is more than 1, this is the case of over damping. If C by Cc is less than 1, this is the case of under damping. Now we see what about the amplitude. In the case of that, we say we started with this equation, we discussed about that point, and one point as I already shown here, okay, that you have E minus C by 2m. So that means this A can be taken, this term can be written in terms of sin omega t, cos omega t. So you have the amplitude term, that means you can write x is equal to something like x0, you can always have some term. So this is x0 E minus C by 2mt, and then maybe that inside you may have sin omega t and this thing. I am not writing that term. So x is equal to basically x0 E minus tau omega n into t. That term is E minus, this is the thing. So this is the thing, tau omega n. Now if we have, in this case, if there is a 0 damping, tau is 0, then x is equal to x0, that means amplitude remains constant. But if tau is that some number, then it will be exponentially decreasing. Therefore the amplitude remains, keeps on decreasing in exponential fashion. It never becomes 0, but it keeps on decreasing. Now this is the thing. So this is a profile, and this is what this happened. Now frequency of damped oscillation is equal to omega d is equal to 2 tau divided by Td. This is Td, that is omega n 1 minus tau square. Not tau, this is basically zeta, that is like that. Okay, so this is the amplitude keeps on decreasing exponentially as t tends to infinity. The amplitude tends to 0. So that way, that is, then damped motion will take place, and this is how that it will be covered. Okay. Now let us, having discussed about the free and forced vibration, let us discuss that simple cases what you have learned. let me just see that this is spring mass system. What you have done here, omega n is equal to under root k by m, right? What happens if we put two springs here? What type of equations you will get? This is m, this is m. In this case, suppose you displace it by distance x from here. Now mx double dot is equal to minus, this is k1 k2 minus k1 x1 x minus k2 x. If you make a free body diagram of this mass, okay, you indicate, you can say, you see, minus k1x and minus k2x. These will be the forces. So you have mx double dot minus kx minus k2x. That means mx double dot plus k1 okay. So it is the same type of equation. Now here compare this equation with previous that equation, mx dot plus kx equal to 0. So we see that we need not solve this again, we can say equivalent, basically this thing. So equivalent k, in this case we can say k equivalent is equal to k1 plus k2. So these two springs are in parallel, so therefore their stiffnesses gets added up. That is the type of thing. Now let us see the another case, that in which there is a mass and this is the mass m, this is k1, this is k2, and it is x. If we give that this x, so here let us make the free body diagram of this. Now let us say that this point displaces by basically y. So we have that if we see mx double dot, Newton's law applied, mx double dot is equal to minus k2 x minus y. So we can say, because this mass is this one, separately we can draw, and this is accelerating, so its acceleration is mx is x double dot, and this is mass. Now here this becomes k2 x minus y, basically, because this end of the spring has moved at a distance x, the other end has moved at a distance y. So mx double dot is equal to minus k2 x minus y. Now if you consider the spring k1, so this is k1 spring is there. Now this gets stretched by an amount y, so this force is minus k1, so minus k1 y. So now consider that spring K2 is subjected to a force minus K2x minus y, and this is same as, it must be the same because the force is getting transmitted. So from transmissibility principle, that is, this is same is basically, this is K2 plus and this is K1, this is y. That means K1y is equal to K2x minus y, K2x minus K2y. Therefore, y is equal to K2x divided by K1 plus K2. Therefore, your equation becomes mx dot is equal to minus K2x K2x minus K2y. So this becomes K1 plus K2 and this becomes K2x. So this is minus mx dot is equal to minus K2x, and this is now we will say that this is K2x minus K2y, this is K1 plus K2 is equal to K2x divided by K1 plus K2. This is y and this is x minus K2x divided by K1 plus K2. So simplify it, this will come out to be minus K1 K2 divided by K1 plus K2 x. Compare it with mx is equal to mx dot is equal to minus kx. So therefore we see that in this case the equivalent K equivalent comes out to be K1 plus K2 divided by K1 plus K2. Therefore, one by K equivalent is equal to 1 by K1 plus 1 by K2. So when these springs are in series, then they are added in this fashion. You can easily see that K equivalent cannot be, suppose you have K1, K2, and in this case K1 is, let us say, greater than K2, then naturally the K equivalent will be even cannot be more than K2 actually. So therefore when they are in the series, then equivalent stiffness in fact reduces. Okay, so this is the type of this thing. Now, so when the springs are in series, then this is 1 by K equivalent, 1 by K1 plus 1 by K2. Now let us see that, say for example this case, now here this is K1, this is K2. How should I solve this problem? Now this is the x position from here. Now if this mass is displaced by some distance, therefore K1 mx dot, so free body diagram, let us say making the free body diagram, this is m, this is minus k1x, this spring gets compressed because suppose this gets stressed by x, another spring gets compressed by x. So therefore this becomes k2x, so minus k2, this is k2x. Okay, let me make k1x like that, this is k2x. This gets compressed, so it puts opposite force. So when we consider the force coming on the mass, this has to be put like this, k2x. So therefore mass mx dot x dot is equal to minus k1 x minus k2x. That means minus k1 plus k2x. So equivalent stiffness is basically minus k1 plus k2. So therefore, considering that springs are in parallel does not mean that physically they will look, that in the same line and this thing, that they are basically like this, because they undergo same type of displacement. If they are going the same amount of displacement, then they are in parallel. If they are undergoing the different displacement, then they are not in parallel, they are in series. Here they are in series because here this is the thing, and then after that another spring is there, it gets stretched, so they are in the series. This goes by some x amount, this point with respect to this point it may move some another this distance, so it is like that. And therefore if you have finally this type of problem, okay, k1, k2, k3, here all these springs are in parallel, therefore equivalent stiffness is k1 plus k2 plus k3, and omega n will be equal to under root m divided by k1 plus k2 plus k3 divided by m. So this is what that this one. So by this you can now you can find out the vibrations of this one. So we have discussed about the free vibrations in absence of damping. We also have discussed the vibrations in presence of damping. Now in presence of damping we have, you can easily derive that in presence of damping the natural frequency will be omega times under root 1 minus zeta square, that is damping. So therefore the natural frequency, that undamped natural frequency, reduces by that thing, and this is what that this